Welcome everyone to another deep dive into the world of data infrastructure. Today we're going to talk about something that's become absolutely critical for modern applications, time series databases. And not just any time series database, we're looking at QuestDB. You know, I've been following the time series space for a while now, and it's fascinating to see how much it's evolved. We're moving away from those heavy general-purpose databases that just weren't built for this kind of workload and toward purpose-built engines that actually understand. QuestDB positions itself as the fastest open-source time series database for demanding workloads, and that's a pretty bold claim, right? What really caught my attention is that it's SQL native, which is a huge deal for teams that don't want to learn yet another query language. And it's built specifically for those ingest-heavy, low-latency time series use cases where every millisecond counts. The database is engineered for low latency using a column-oriented time-partition storage engine with memory-mapped files and vectorized execution to support high-throughput ingestion and millisecond-level analytical queries. So let's just jump right in and see what makes this thing tick. I'm looking at the numbers here, and wow, we're talking about 1.36 million rows per second peak ingestion. That's mind-boggling. Let me put that in perspective for a moment. That's over 1 million individual data points streaming into the database every single second, and it's 3.3 to 36 times faster than InfluxDB. I mean, that's not just a little bit faster, that's in a completely different league. What's really impressive is the efficiency in benchmark tests using 4 threads. QuestDB was 1.7 times faster than ClickHouse, 6.5 times faster than InfluxDB, and 6.6 times faster than TimescaleDB. And it achieves this maximum throughput with just 4 workers, while other systems need significantly more CPU resources to reach their peak performance. That's what I call hardware efficiency. And it's all under the Apache 2.0 license, fully open source, with over 17,000 GitHub stars at this point. That's a lot of community trust and adoption. The benchmarks are public, which I really appreciate. You can actually go and reproduce them yourself. And the community is active with regular releases, so, you know, it's not just a stagnant project. There are 136 contributors and over 1,000 forks. This is a living, breathing open source ecosystem. Okay, so why do we even need a purpose-built time series database? That's a really good question. I think a lot of people, when they first start out, they just reach for what they know. Maybe a relational database like PostgreSQL, or maybe they go with a NoSQL solution. But the problem is these general purpose databases hit some pretty serious failure modes when you throw time-stamped append-only workloads at them. Let me walk you through each one. The first problem, relational databases just choke on the write rate. Think about it. You've got this B-tree index structure, and under append-only writes at millions of rows per second, those indexes just thrash. You get vacuum overhead, wall checkpoint, bottlenecks, lock contention. It's a mess. The system spends more time managing the index than actually storing your data. Second problem, NoSQL databases often trade SQL for scale. You get write scaling, sure, but then you're stuck with custom query languages and weak analytics. Time-bucketed aggregation becomes this hand-rolled application code that you have to maintain and debug, and we all know how fun that is. Not very. And then there's the third problem, generic OLAP engines. They're optimized for star schemas and complex analytical queries, not for designated timestamp ordering, latest value lookups, or interval scans. They just don't think in time the way a time series database should. The query patterns are fundamentally different. QuestDB's answer to all of this is elegant. Append-optimized columnar storage where rows are physically sorted by a designated timestamp and partitioned by time-aware SQL extensions like spellable by, latest on, and ASOF join as first-class keywords. And wire protocol compatibility so you can drop it in without rewriting your entire stack. So if your data has a timestamp and you query by time, you really want a time series database. All right, let's get into the engine and SQL. This is where QuestDB really gets its speed. We're talking about columnar storage, SIMD vector execution, 0GC Java, and XQL extended for time. The system is built from scratch with a 0GC Java core and focused C++ and Rust components in a compact codebase optimized for cache locality and predictable tail latency. The architecture implements a row-based write path for maximum ingestion throughput and a column-based read path for maximum query performance. This dual-path approach is actually quite clever. You get the best of both worlds. High-speed ingestion doesn't compromise query performance and vice versa. Let me break down each of the 5 design pillars that make this possible. Now, the SQL extensions are really where QuestDB shines. It speaks standard ANSI SQL, but on top of that, it adds purpose-built keywords for time series workloads. These turn awkward 20-line window function gymnastics into single clause reads. The designated timestamp column is the key here. Rows are physically sorted by it, so time-bucketed operations are incredibly cheap. Let me explain each of these extensions in detail. First, Spemple by. This aggregates data into evenly spaced time buckets aligned to the designated timestamp. It's shorter and faster than equivalent group by date trunk patterns and supports calendar alignment with time zones and DST. You can do hourly averages, daily summaries, monthly maximums, all with a simple clause. And it supports interpolation for missing intervals with the fill keyword. You can fill gaps with null, previous values, linear interpolation, or constant values. This is incredibly powerful for downsampling and summarizing large datasets. Second, latest on this returns the most recent row per partition key using the designated timestamp's physical sort order to avoid a full scan. It's the QuestDB equivalent of PostgreSQL's detrumpix on and the window function patterns commonly used in other dialects. For example, you can get the latest trade for each trading symbol with a simple query. It's perfect for getting the current state of each device or sensor in an IoT deployment. Third, ASOF join. This is the most common time series join in QuestDB. It matches each row in one time series table with the most recent row in another table, whose timestamp is at or before the left row's timestamp. Typical use cases include attaching the prevailing market quote to each trade, looking up the current sensor calibration for each reading, or enriching events with the latest known state. You can also specify a tolerance clause to reject matches that are too old. And there's also a tick interval syntax that extends where with a concise interval format. It compiles to optimized interval scans and is both shorter and faster than DATAD and now arithmetic. On QuestDB Enterprise, you can even use Exchange calendars so the database knows about market holidays and early closes. When it comes to ingestion, QuestDB accepts writes over 3 protocols. You can pick the one that matches your stack. No client rewrites, no schema ceremony, no migration downtime. Let me walk through each one. First, the InfluxDB line protocol over TCP or UDP. This can handle about 4 million rows per second per node. It's a drop-in replacement for InfluxDB, so tools like Telegraph and FluentD work unchanged. You just send lines like trade symbol BTC USD price equals 511234.5, volume equals 1.2 with a timestamp. The first-party clients are the fastest way to insert data and are the recommended choice for production deployments. They provide automatic table creation, concurrent schema changes, optimized batching, health checks, and automatic write retries. The ILP protocol is insert-only and bypasses SQL insert statements, achieving significantly higher throughput. Second, the PostgreSQL wire protocol on port 8812 AnyPrate. Any PostgreSQL client can connect directly using standard SQL insert and copy semantics. This is great for application backends and ORM integration. But it's worth noting that for data ingestion, the first-party clients with ILP are recommended over PGWire. PGWire should primarily be used for querying data. Third, the HTTP REST API for ad hoc queries and simple writes. The web console on port 9000 provides a built-in interface for data exploration and query execution. You can also use it for bulk imports and exports of CSV files, so you have a lot of flexibility depending on your use case and existing tooling. Let's talk about performance and use cases. The numbers from public benchmarks are really impressive. QuestDB is 3.3 to 36 times faster than InfluxDB, and the gap actually widens at scale. When running on 4 threads, QuestDB beats ClickHouse by 1.7 times, InfluxDB by 6.5 times, and TimescaleDB by 6.6 times. Compared to KDB+, QuestDB is about 4.4 times faster, and compared to TimescaleDB, it's about 41 times faster. These aren't just marketing numbers, they're publicly reproducible using the time series benchmark suite, which is a collection of tools used to generate datasets and benchmark read and write performance. QuestDB achieves about 4 million rows per second ingestion throughput. The database is optimized for both throughput and latency, with batched writes handling about 400,000 rows per second per connection, and single row writes handling 60,000 to 80,000 rows per second. Looking at the performance charts from the TSBS-style ingestion benchmarks on the QuestDB blog, all numbers are publicly reproducible. The benchmarks depend on hardware, schema, and configuration, so you should always read the methodology, but the trends are clear across multiple test scenarios. QuestDB achieves maximum ingestion throughput with just 4 worker threads, while other systems need significantly more CPU resources to reach their peak throughput. This means QuestDB is not only faster, but also more hardware efficient. You get better performance with fewer resources. That translates directly to lower cloud costs and smaller hardware footprints. The gap between QuestDB and other databases actually widens at scale. As you increase the data volume and the number of devices or sensors, QuestDB maintains its performance advantage. This is critical for production workloads where data volumes are constantly growing. Financial market data is the canonical high-throughput time series workload. Every quote, trade and order book mutation is timestamped first, write-heavy, and demands point-in-time joins. QuestDB has replaced KDB Plus at several trading firms for intraday tick storage. It offers ANSI SQL ergonomics at a fraction of the licensing cost. Let me walk through the specific use cases. Real-time tick capture with ILP ingestion at millions of ticks per second, persisted to the columnar store. OHLC bar aggregation with spammable by for 1 minute, 5 minute, or 1 hour candlestick buckets. Order book reconstruction with ASOF join to recover the book state at any historical instant. And backtesting and market replay with sub-millisecond read latency, one quant team said, and I quote, "We replaced KDB Plus for intraday tick storage. QuestDB gives us ESQL and roughly 1/10 the TCO. That's a massive cost saving. For crypto trading, QuestDB enables continuous, low-latency multi-exchange ingestion and native SQL order book analytics. You can aggregate multi-exchange market data and query it in real time, measure P&L and reaction latency by venue and strategy, and backtest with open-source data frames. Latin America's largest stock exchange, B3 in Brazil, uses QuestDB with 99.9% uptime. One Trading's chief security officer said, "QuestDB is an essential part of our trading platform, giving us a high-speed, scalable store for billions of trades that we can query in real time." IoT and infrastructure monitoring workloads share the same shape, millions of devices emitting tag metrics at high frequency, queried through downsampled rollups and latest value lookups. QuestDB handles the cardinality that breaks naive time series databases. You can use Telegraph with the InfluxDB line protocol as a drop-in replacement for InfluxDB with no agent config changes, fleet telemetry with high cardinality tag sets like device ID, region, and firmware, no index bloat. Industrial sensors, you can do spulpal by 1-minute rollups for operator dashboards while retaining raw data for forensics. And for infrastructure metrics, there's a Prometheus exporter and a Grafana Day2 Saucers plugin for sub-second panel queries. A typical query might be, select device ID, AVG TPU Pacienti from metrics where TS greater than datad, H-1. Now spulpal by 1.0 partition by device ID. This gives you the 1-minute average CPU per device for the last hour. Simple, powerful, and fast. QuestDB is also used in aerospace for high-rate telemetry ingestion and real-time analysis for flight test and mission-critical systems. It can handle high cardinality sensor streams and evolving schemas. With multi-tier storage for petabytes of flight test data, you can correlate sensor streams with ASOF joins for root cause and anomaly analysis. In the energy sector, QuestDB ingests and analyzes sensor data from hundreds of thousands of endpoints in real time. It serves as a modern replacement for legacy historians with SQL-first simplicity and seamless interoperability with SCADA, Telegraph, MQTT, and Postgres tooling. Now let's talk about operations and the ecosystem. How do you actually run this thing? Well, you have options. You can run it as a single binary in a container via a Helm chart on Kubernetes, or use the fully managed cloud offering. The same engine, same SQL, same open on disk format. QuestDB Enterprise builds on top of the open source core, adding features like high availability, advanced security, RBAC, automated backups, and multi-tier storage. The storage model is organized into 3 tiers that handle data across its entire lifecycle. Tier 1 is the hot ingest wall, durable by default. Tier 2 is the real-time SQL on live data in the native columnar format. Tier 3 is cold storage in Apache Parquet, which is open and queryable by any tool. This delivers predictable costs, interoperability with AI and ML tooling, and zero lock-in. Let me walk through the deployment options in more detail. The Docker approach is the simplest. You just run a single container with all 3 ports exposed. The web UI is on port 9000, the PostgreSQL wire protocol is on 8812, and the InfluxDB line protocol is on 9009. Official Docker images are available for both AMD 64 and ARM 64 architectures. The Docker entry point script handles environment variable mapping to QuestDB properties. There are also native binaries for Linux, macOS, and Windows with no JVM installation required. The static binary includes everything you need for Kubernetes. There's an official Helm chart with persistent volumes, a sidecar telegraph, and a Prometheus exporter. QuestDB supports reading sensitive configuration values directly from mounted secret files. And if you don't want to manage it yourself, there's QuestDB Cloud on AWS and GCP with auto-scaling, S3-backed open storage, pausing and snapshots. It also includes role-based access control and built-in metrics with a Prometheus exporter. QuestDB Enterprise supports single sign-on in the web console and high availability with read replicas and multi-primary configurations. The integrations and community are also worth mentioning. QuestDB plugs into the tools you already run. There are first-party clients for C++, .NET, Go, Java, Node.js, Python, and Rust. These clients use the InfluxDB line protocol for high-throughput ingestion with automatic table creation, concurrent schema changes, optimized batching, health checks, and automatic write retries. You can also use message brokers like Kafka and Flink with a QuestDB Kafka connector built on the Kafka Connect framework, or import CSV files through the web console. There's a QuestDB demo instance that's hosted, fully loaded, and ready to go for quick exploration. The community is thriving. Over 17,000 GitHub stars, 136 contributors, an active Slack community, and regular releases. The documentation is comprehensive and the community is responsive. It's an exciting time to be involved in open source time series databases. So to wrap this up, getting started with QuestDB is incredibly simple. You just pull and run the Docker container, open the web UI on port 9000, and you're ready to go. You can write your first row using the InfluxDB line protocol over TCP, or use any PostgreSQL client. The web console is built right into the engine for running SQL statements, bulk loading CSV files, and displaying monitoring dashboards. It's XQL native, it uses open formats like Parquet and Arrow, and it's built for time. The combination of columnar storage, SMD vectorization, zero-GC Java, and those time-aware SQL extensions makes it a compelling choice for anyone dealing with high-velocity timestamp data. Whether you're in fintech, IoT, observability, aerospace, energy, or any other domain that deals with time series data, QuestDB is definitely worth a look. The performance numbers speak for themselves, and the open source model means you can try it out without any commitment. The code base is built from the ground up with no dependencies and zero garbage collection. So I'd encourage you to check it out, run the benchmarks yourself, and see what it can do for your workloads. Thanks for joining me on this deep dive into QuestDB. I hope you found it informative and maybe even a little inspiring. Time series data is everywhere, and having the right tool to handle it can make all the difference. QuestDB is pushing the boundaries of what's possible with open source time series databases, and it's exciting to see where this project is headed. If you have any questions or want to share your own experiences with QuestDB, I'd love to hear about them. The community is active and welcoming. Until next time, keep building, keep querying, and keep thinking about time. Thanks for listening.